The star that refuses to become a black hole. Somewhere in the universe right now, a massive star is dying. Not quietly and not slowly. Deep within its core, gravity is crushing matter with a force so intense that atoms themselves are breaking apart. The star is more than 20 times the mass of our sun, and the weight of all that matter is collapsing inward. The core is shrinking rapidly. Electrons are being squeezed into protons, and matter is transforming into something entirely different. And according to everything we know about gravity, the story should end in only one way: a black hole. Gravity should win. The collapse should continue relentlessly until the entire core disappears behind an event horizon, becoming one of the most mysterious objects in the universe. But that is not what happens. Instead, the collapse stops. The star does not become a black hole. Something pushes back. Something powerful enough to resist the crushing weight of more than a solar mass compressed into a sphere barely 20 kilometers across. Something capable of stopping gravity at nearly its most extreme. And that something comes from one of the strangest laws ever discovered in physics. A rule born not in the study of stars, but in the bizarre world of quantum mechanics. Well, to understand why neutron stars exist, why they do not collapse immediately into black holes, we have to follow the story from the beginning, back to the moment when the star itself was alive. A star that burns too bright. Massive stars live fast. While our sun burns slowly and steadily, expected to shine for roughly 10 billion years. Truly massive stars follow a very different path. They are cosmic furnaces. Yet a star 20 times the mass of the sun releases energy at an astonishing rate, sometimes hundreds of thousands of times brighter than our star. If such a star replaced the sun in our solar system, Earth would not merely become warmer. It would be instantly sterilized. Oceans would boil. The atmosphere would escape into space. Life would vanish in moments. But this incredible brightness comes at a cost. Massive stars consume their fuel at an extraordinary pace. Where the sun can shine for billions of years, a star 20 times more massive may live for only about 10 million years. On cosmic timescales, that is barely an instant. The universe itself is nearly 14 billion years old. A massive star lives for less than 1,000th of that time. It is born, it burns brilliantly, and then it dies. The delicate balance. Inside every star. For most of its life, a massive star exists in a delicate balance. At the center of the star, nuclear fusion is taking place. Hydrogen atoms collide and merge, forming helium. During this process, a tiny fraction of mass is converted directly into energy, following Einstein's famous equation, E equals mc squared. Even a tiny loss of mass produces an enormous amount of energy. This energy creates pressure, intense outward pressure pushing against gravity, and gravity is always pulling inward. Every atom in the star is attracted toward the center by the gravitational pull of every other atom. The outward pressure from nuclear fusion fights against this collapse. The result is a stable equilibrium. Physicists call this balance hydrostatic equilibrium. As long as fusion continues, the star survives. Gravity pulls inward, energy pushes outward, and the star remains stable. But this balance cannot last forever. Eventually, the star runs out of fuel. The race toward catastrophe. When hydrogen in the core is exhausted, the outward pressure weakens. Gravity immediately begins to compress the core. But this compression has an unexpected effect. As the core shrinks, it heats up. The temperature rises dramatically. Eventually, it becomes hot enough to ignite a new fusion reaction. Helium begins fusing into carbon. The star survives. For a while, but the pattern that follows becomes increasingly desperate. Each new fuel burns faster than the last. Hydrogen burning may last 10 million years. Helium burning lasts roughly 1 million years. Carbon burning continues for only thousands of years. Neon burning may last 1 year. Oxygen burning, about 6 months. And the final stage, silicon fusion, may last only a single day. Think about that. A star that spent millions of years peacefully burning hydrogen consumes its final fuel in less than 24 hours. This is not a gradual ending. It is a runaway process. The star is racing toward collapse. The iron barrier. During these final stages, the interior of the star develops a layered structure. Much like an onion, at the center lies the newest element being fused. Around it are shells where earlier elements continue burning. Near the end of the star's life, the layers may look something like this: iron at the center, surrounded by silicon, then oxygen, then neon, then carbon, then helium, and finally hydrogen at the outermost layers. Each shell is trying desperately to produce energy and maintain the outward pressure that keeps gravity under control. But eventually, the process reaches a dead end. Iron. Iron is special in nuclear physics. Unlike lighter elements, fusing iron does not release energy. Instead, it requires energy. Iron sits at the peak of what physicists call the binding energy curve. It is the most stable atomic nucleus that can exist, and that means the star has nowhere left to go. Fusion can no longer save it. The moment everything fails. As silicon fusion continues in the outer shells, more and more iron accumulates in the center. The iron core grows heavier, denser, hotter, but it produces no energy. Eventually, the core reaches a critical threshold, about 1.4 times the mass of the Sun. At this point, something extraordinary happens, and a form of pressure that had been quietly supporting the core suddenly fails. This pressure is not produced by heat. It does not come from nuclear fusion. It arises from the strange rules of quantum mechanics, and when the core exceeds this limit, gravity overwhelms that pressure completely. The collapse begins. Not slowly, not gradually, but catastrophically. An object roughly the size of Earth suddenly shrinks to a sphere only 20 kilometers wide, and it happens in less than a quarter of a second. Matter falls inward at speeds approaching 75,000 kilometers per second. Atoms are destroyed. Electrons merge with protons. And the core of the star transforms into something that has never existed before. A star made almost entirely of neutrons. A neutron star. But this transformation raises an even deeper mystery, because even after such a catastrophic collapse, gravity still should not be finished. The mass of the core is enormous. The density is unimaginable. By every intuitive expectation, the collapse should continue. And yet, it doesn't. The neutron star remains stable. Something is holding it up. Something powerful enough to resist gravity at nearly its strongest. To understand what that force is, we must leave the world of stars for a moment and dive into the strange and counterintuitive rules that govern the quantum universe. The quantum rule that stops gravity. At this point in the story, something deeply puzzling has happened. A massive star has collapsed. Its core has been crushed from the size of Earth to a sphere only about 20 kilometers across. The density is so extreme that atomic structure itself has been destroyed. Electrons and protons have fused together, forming a dense ocean of neutrons. Gravity is stronger here than almost anywhere else in the observable universe. And yet, the collapse stops. The neutron star remains stable. Gravity, the force that shapes galaxies and bends space-time, has been halted. So what could possibly stop it? The answer lies not in astrophysics, but in the strange microscopic laws governing the particles that make up matter itself. To understand what holds up a neutron star, we must go down to the smallest scales of reality, into the quantum world. Two families of particles. In the universe, and every fundamental particle belongs to one of two families. There are no exceptions. Every particle that has ever existed falls into one of these two categories. The first family is called fermions. The second family is called bosons. At first glance, this distinction might sound like an abstract classification invented by physicists, but in reality, it determines almost everything about how matter behaves. Fermions include particles such as electrons, protons, and neutrons. These are the particles that make up ordinary matter. Everything around you, the air you breathe, the ground beneath your feet, the atoms in your body, is built from fermions. Bosons are different. They include particles like photons, which carry light, and gluons, which bind quarks together inside atomic nuclei. These particles transmit forces, but the most important difference between these two families is not what they do. It is how they behave when many of them occupy the same space. Social particles and antisocial particles. Bosons are surprisingly cooperative. In fact, they can occupy the exact same quantum state without any restriction. You can pile millions, even billions, of bosons into a single identical state, and they are perfectly happy to do so. This is why lasers work. Inside a laser beam, enormous numbers of photons exist in exactly the same quantum state, as they all have the same energy, the same frequency, the same direction, the same phase. They move together like a perfectly synchronized wave. Bosons actually prefer to share states. They cluster together. But fermions are completely different. Fermions refuse. They cannot share the same quantum state, not under any circumstances, not sometimes, not usually, never. This rule is one of the most fundamental laws in all of physics. It is called the Pauli Exclusion Principle, the rule that builds the universe. The Pauli Exclusion Principle was discovered in 1925 by the Austrian physicist Wolfgang Pauli, and its consequences are extraordinary. The rule is simple. No two identical fermions can occupy the same quantum state at the same time. That might sound technical, but this rule is the reason atoms exist. Inside an atom, electrons occupy orbitals, regions where they are most likely to be found. The lowest energy orbital can hold only 2 electrons. Once those states are filled, additional electrons must move to higher energy levels. This creates the layered structure of atoms. It determines the periodic table. It determines the chemistry of every element. Without the Pauli Exclusion Principle, all electrons would collapse into the lowest possible energy state. Every atom would behave the same. There would be no chemical diversity, no molecules, no solids, no liquids, no life. In a very real sense, the structure of the entire universe emerges from this one prohibition. Fermions refuse to be identical. The origin of degeneracy. Pressure. Now imagine compressing a large number of fermions into a smaller and smaller space. At first, the particles occupy the lowest energy states available, but as more fermions are forced into the same region, the available states begin to fill up. Because they cannot share states, each additional particle must occupy a higher and higher energy level. Eventually, some particles are forced into extremely energetic states. These high-energy particles possess large momentum, and particles with high momentum push outward. This creates a form of pressure. But unlike ordinary pressure, this pressure does not come from heat. It comes purely from the Pauli Exclusion Principle. Physicists call this degeneracy pressure. Even at absolute zero temperature, a degeneracy pressure still exists, even when particles have no thermal motion at all. It is a purely quantum mechanical force. A pressure created by the simple fact that fermions refuse to occupy identical states. Degeneracy. Pressure in white dwarfs. This quantum pressure already plays an important role elsewhere in the universe. Consider a white dwarf. When a star similar to our Sun exhausts its nuclear fuel, it sheds its outer layers into space, all forming a glowing shell of gas known as a planetary nebula. What remains is the exposed core, a dense object roughly the size of Earth containing about the mass of the Sun. Fusion has stopped. The star is no longer producing energy, and yet it does not collapse. The reason is electron degeneracy pressure. Electrons in the white dwarf are packed extremely tightly. Because they cannot share quantum states, they push outward against gravity. This quantum pressure supports the entire star, but this support has a limit. As the mass increases, gravity compresses the electrons more and more tightly. Eventually, the electrons begin moving close to the speed of light. At that point, the pressure can no longer increase fast enough to resist gravity. The star becomes unstable. This critical threshold is known as the Chandrasekhar limit, about 1.4 times the mass of the Sun. Beyond this mass, electron degeneracy pressure fails, and the star collapses. The birth of neutron degeneracy pressure. During the catastrophic collapse of a massive star, electrons are forced into protons. They combine through a process known as electron capture. The result is a sea of neutrons. And neutrons are also fermions, which means they obey the Pauli Exclusion Principle as well. But neutrons are far heavier than electrons. A neutron is roughly 1,800 times more massive than an electron. This difference changes everything. Because neutrons are heavier, they can be compressed to far higher densities before becoming relativistic. This means neutron degeneracy pressure can support far more mass than electron degeneracy pressure. It is this pressure that halts the collapse of a neutron star. The neutrons, packed at densities similar to atomic nuclei, refuse to occupy identical states. They push outward, gravity pushes inward, and for stars below a certain mass, these forces balance perfectly. The neutron star survives. A battle between two fundamental laws. Inside a neutron star, two of the most powerful forces in nature confront each other. Gravity tries to crush the star further. Quantum mechanics resists. The Pauli Exclusion Principle forces neutrons into increasingly energetic states. Those energetic neutrons generate immense outward pressure. The result is a delicate equilibrium, a balance between gravity and quantum mechanics. A balance that allows a star containing more mass than our Sun to exist as an object only 20 kilometers across. It is one of the most extraordinary structures in the universe. But this equilibrium does not exist forever. There is a limit. If the mass grows too large, even neutron degeneracy pressure cannot resist gravity, and when that happens, the collapse begins again. Inside a neutron star. A neutron star may appear simple from the outside, a sphere only about 20 kilometers across. But inside, it is one of the most complex and exotic objects in the universe. The matter inside a neutron star is compressed to densities so extreme that nothing remotely similar exists anywhere else in nature. Not on Earth, not inside ordinary stars, not even inside atomic nuclei. To understand just how strange a neutron star truly is we need to take an imaginary journey downward, layer by layer, from its thin outer surface, all the way to its mysterious core. The surface. Gravity beyond imagination. The very surface of a neutron star is already an environment beyond human comprehension. The gravitational pull there is roughly 200 billion times stronger than on Earth. If you somehow dropped an object from a height of only 1 meter above the surface, and it would strike the ground at nearly 7 million kilometers per hour. That is faster than most spacecraft ever built. But even that comparison hardly captures the reality. No human could approach the surface. Long before you reached it, the difference in gravitational pull between your head and your feet would tear you apart atom by atom. Physicists call this tidal spaghettification. Matter is stretched into thin strands by the immense gravitational gradient, and yet the neutron star itself remains intact, held together by the very quantum forces we explored earlier. A thin but extreme atmosphere. The outermost layer of a neutron star is its atmosphere. Despite the star's enormous gravity, this atmosphere is astonishingly thin. In many cases, it may be only a few centimeters thick, but the density here is already far greater than anything we experience on Earth. The atoms in this atmosphere are stripped of their electrons. The matter exists as an extremely hot plasma. Temperatures can reach over 1 million degrees Celsius shortly after the neutron star forms. The exact composition depends on what material has fallen onto the star from space. It may contain hydrogen, helium, or heavier elements from the surrounding debris of the supernova that created the star. Even this fragile layer provides astronomers with valuable clues. By studying the light emitted from the surface, us scientists can measure the neutron star's temperature, gravity, and chemical composition. The outer crust, the strongest material in the universe. Just beneath the atmosphere lies the outer crust. This region extends downward for several hundred meters. Here, atomic nuclei are arranged in an incredibly dense crystal lattice. Imagine a metal, but compressed to unimaginable densities. The nuclei sit in orderly positions like atoms in a crystal. But the pressure here is so immense that the nuclei are squeezed closer together than ever before. Free electrons move between them like a fluid. This combination creates an incredibly rigid structure. In fact, the crust of a neutron star may be the strongest material in the entire universe. Simulations suggest it could be billions of times stronger than steel. Yet even this extraordinary crust occasionally cracks. When it does, the resulting starquake can release bursts of radiation detectable across the galaxy. The neutron drip line. As we descend deeper into the crust, the pressure increases dramatically. Eventually, something remarkable happens. Atomic nuclei become so overloaded with neutrons that they can no longer hold them all. Neutrons begin to escape. They literally drip out of the nuclei. Physicists call this boundary the neutron drip line. Below this depth, the interior of the star becomes something entirely new. The crust is now a strange mixture of three components: extremely neutron-rich nuclei, a sea of free neutrons, and a background of electrons. No environment like this exists naturally anywhere else in the universe. This strange state of matter only appears under the crushing gravity of neutron stars. The inner crust, a quantum ocean. Deeper still, the number of free neutrons increases rapidly. Eventually, they begin to behave in an extraordinary way. The neutrons pair up, and when they do, they can enter a state known as a superfluid. A superfluid is one of the strangest states of matter ever discovered. It flows with zero viscosity, no friction, no resistance. If you could somehow stir a container of superfluid, it would continue spinning forever. Inside a neutron star, vast oceans of neutrons exist in this superfluid state. And this superfluid plays a crucial role in one of the most fascinating phenomena observed in neutron stars: pulsar glitches. The mystery of pulsar glitches. Some neutron stars rotate extremely rapidly, hundreds of times per second. When these rotating neutron stars emit beams of radiation that sweep across Earth, we observe them as pulsars. Their signals are astonishingly regular, so regular that pulsars rival atomic clocks in precision. But occasionally something strange happens. The pulsar suddenly spins slightly faster. Its rotation jumps abruptly. This event is called a glitch. The leading explanation involves the superfluid interior. Inside the star, the superfluid neutrons rotate by forming tiny quantum vortices. These vortices can become pinned to the crust. Over time, the crust slows down slightly due to electromagnetic radiation. But the superfluid interior continues spinning at its original rate. Eventually, the vortices break free. Angular momentum is transferred to the crust, and the star suddenly speeds up. The glitch is detected instantly by radio telescopes on Earth. These tiny timing irregularities reveal the presence of superfluid matter deep inside neutron stars. The outer core, nuclear matter. Below the inner crust lies the outer core. Here, the pressure becomes so intense that atomic nuclei no longer exist. The matter becomes a dense fluid composed mostly of neutrons, with a small number of protons and electrons mixed in. Roughly 95% neutrons, about 5% protons, and just enough electrons to balance the electrical charge. Both the neutrons and protons are believed to form superfluids and superconductors. This means electrical currents can flow without resistance, and that property helps sustain the neutron star's enormous magnetic field. These magnetic fields can be trillions of times stronger than Earth's, among the strongest fields anywhere in the universe. The inner core, a frontier of physics. At the very center of the neutron star lies the inner core. And here our knowledge begins to fade. The densities may reach 5 to 10 times greater than atomic nuclei. No laboratory on Earth can reproduce such conditions. Even the most powerful particle accelerators cannot create matter compressed this intensely for any meaningful duration. So physicists rely on theory, and several possibilities have been proposed. One idea is that neutrons themselves break apart. Remember, neutrons are not fundamental particles. They are made of 3 quarks. Under sufficient pressure, the boundaries between neutrons may dissolve. The quarks could form a new state of matter known as quark matter, a vast ocean of free quarks moving through the star's core. Another possibility involves something even stranger: matter containing strange quarks. This hypothetical state is called strange matter. Some physicists believe it may actually be more stable than ordinary nuclear matter. If that is true, entire stars made of strange quark matter could exist. These would be known as strange stars. But at present, we simply do not know. The interior of neutron stars remains one of the greatest unsolved mysteries in modern physics, a city-sized atomic nucleus. Despite all this complexity, the simplest way to imagine a neutron star is surprisingly elegant. Think of it as a gigantic atomic nucleus. An ordinary atomic nucleus contains protons and neutrons packed together at nuclear density. A neutron star contains matter at roughly the same density, but instead of being a few femtometers across, it spans 20 kilometers. It is essentially a nucleus the size of a city, the largest atomic nucleus in the universe, a structure where gravity and quantum mechanics meet at unimaginable scales. And yet, even this astonishing object still lives on borrowed time, because there is a limit to how much mass a neutron star can support, a precise threshold beyond which quantum mechanics can no longer resist gravity. Beyond that limit, the star collapses once more. And this time, nothing stops it. Pulsars, magnetars, and the most extreme physics in the universe. A neutron star is already one of the strangest objects nature has ever produced, but some neutron stars take extreme physics even further. They spin faster. They generate stronger magnetic fields. They release bursts of energy that can briefly outshine entire galaxies. And through these phenomena, neutron stars reveal themselves to us across vast cosmic distances, the birth of a cosmic lighthouse. When the core of a massive star collapses during a supernova, something else happens besides the dramatic compression of matter. The star begins spinning faster, much faster. This happens because of a simple rule of physics known as the conservation of angular momentum. You have probably seen this effect before in figure skating. When a skater pulls their arms inward, they spin faster. The same thing happens to a collapsing star. And before collapse, the stellar core may rotate slowly, perhaps once every few days. But when that core shrinks from thousands of kilometers across to only about 20 kilometers, the rotation speed increases dramatically. The newborn neutron star may spin dozens or even hundreds of times per second. That means the entire star is rotating faster than the blades of a helicopter, faster than a jet turbine, faster than almost anything humans have ever built. Pulsars, the universe's most precise clocks. Many neutron stars also possess powerful magnetic fields. These magnetic fields channel charged particles toward the star's magnetic poles. There, the particles are accelerated to extraordinary speeds, producing intense beams of radiation. If the magnetic axis of the neutron star is tilted relative to its rotation axis, those beams sweep through space like the beam of a lighthouse. Every time the beam crosses Earth, we detect a pulse of radiation. These objects are known as pulsars. The pulses can occur every few milliseconds, or every few seconds. But what makes pulsars truly astonishing is their precision. Some pulsars keep time more accurately than the most advanced atomic clocks ever built on Earth. Their pulses arrive with such regularity that astronomers can predict their timing years in advance with incredible accuracy. This precision allows pulsars to serve as natural laboratories for testing the laws of physics. Through pulsars, scientists have confirmed predictions from Einstein's theory of relativity. They have measured the existence of gravitational waves long before direct detectors were built, and they have used pulsars as cosmic navigation beacons across the galaxy. The discovery that changed astronomy. The first pulsar was discovered in 1967 by a graduate student named Jocelyn Bell Burnell. She was analyzing data from a radio telescope when she noticed something unusual, a signal repeating with extraordinary precision. Every 1.337 seconds. At first, the signal seemed so artificial that astronomers jokingly labeled it LGM1, short for Little Green Men. But soon, other similar signals were discovered from different regions of the sky. It became clear that these pulses were not artificial transmissions. They were rotating neutron stars. Today, astronomers have discovered thousands of pulsars scattered throughout the Milky Way. Each one is the spinning remnant of a once massive star. Millisecond pulsars. Stars spinning faster than imagination. Some neutron stars spin even faster. These are known as millisecond pulsars. They can rotate hundreds of times every second. One of the fastest known examples spins 716 times per second. Imagine standing on the equator of such a star. A point on the surface would be traveling at nearly a quarter of the speed of light. That is over 70,000 kilometers per second. If the star spun any faster, the centrifugal force would begin tearing it apart. These extraordinary rotation speeds usually occur in binary star systems. The matter from a companion star gradually spirals onto the neutron star. As this material falls inward, it transfers angular momentum. Slowly spinning neutron stars can be spun up into millisecond pulsars through this process. Magnetars, the strongest magnetic fields in the universe. But rotation is not the only extreme property neutron stars can possess. Some neutron stars generate magnetic fields so powerful that they reshape the very structure of matter. These objects are called magnetars. A typical neutron star might have a magnetic field trillions of times stronger than Earth's. But magnetars push this to an entirely different level. Their magnetic fields can reach 100 trillion times stronger than Earth's magnetic field. These are the most powerful magnetic fields known to exist anywhere in the universe. At such strengths, even empty space behaves differently. According to quantum theory, the vacuum itself becomes slightly polarized by the magnetic field. Light traveling through this region can split into different polarization states, a phenomenon known as vacuum birefringence. Under normal conditions, this effect is almost impossible to observe, but near magnetars, the effect becomes measurable, providing rare confirmation of predictions made by quantum electrodynamics. Yeah. Starquakes and gamma-ray flares. Magnetars also produce some of the most violent explosions known outside of supernovae. Their magnetic fields twist and stress the solid crust of the neutron star. Eventually, the crust can no longer withstand the strain. It fractures. When this happens, the star experiences a starquake. The sudden shift in the crust releases enormous amounts of magnetic energy. In just a fraction of a second, a magnetar flare can release as much energy as the sun emits in hundreds of thousands of years. One such event occurred in 2004 from a magnetar on the far side of our galaxy. Even though it was 50,000 light-years away, the burst briefly affected Earth's upper atmosphere. Satellites detected the surge of radiation. A single neutron star, smaller than a city, produced an explosion powerful enough to disturb our planet from across the galaxy. Natural laboratories for extreme physics. Because of these extraordinary properties, neutron stars provide scientists with unique opportunities to study physics under conditions that cannot be recreated on Earth. They allow us to test ultra-dense nuclear matter, superfluid physics, extreme magnetic fields, relativistic gravity, gravitational waves. In many ways, neutron stars are cosmic laboratories, experiments conducted by nature itself, operating at energies and densities far beyond the reach of human technology. And yet, even with all their incredible properties, neutron stars are not the final stage of gravitational collapse. There is a boundary, a precise limit beyond which even the quantum forces inside a neutron star cannot resist gravity. Beyond that boundary, the star collapses again, this time forming one of the most mysterious objects in the universe. A black hole. The maximum mass of a neutron star. For millions, sometimes billions, of years, a neutron star can remain perfectly stable. Gravity pulls inward with unimaginable force. Quantum mechanics pushes outward through neutron degeneracy pressure. The two forces balance. The star survives. But this balance is not infinite. There is a precise threshold, a point beyond which gravity inevitably wins. Physicists call this boundary the Tolman-Oppenheimer-Volkoff limit. Often shortened to the TOV limit, it represents the maximum mass that neutron degeneracy pressure can support against gravitational collapse. Below this limit, a neutron star can exist. Above it, the star must collapse into a black hole. No known force in nature can prevent that outcome. When pressure becomes gravity. To understand why this limit exists, we need to look at gravity in its most extreme form. In everyday situations, gravity behaves according to the laws described by Isaac Newton. In Newton's theory, gravity depends only on mass. More mass means stronger gravity. Pressure simply resists that collapse. In principle, if you could generate enough pressure, you could support any amount of mass. But neutron stars do not exist in Newton's universe. They exist in the universe described by Albert Einstein. And Einstein's theory of gravity is very different. In general relativity, gravity is not produced by mass alone. It is produced by energy, and pressure is a form of energy. This leads to one of the most counterintuitive results in physics. Inside a neutron star, the pressure that tries to hold the star up also contributes to the gravitational field trying to crush it. In other words, pressure both resists gravity and strengthens gravity at the same time. A runaway feedback loop. Imagine adding more mass to a neutron star. Gravity grows stronger. To resist that stronger gravity, the neutrons must be compressed into higher and higher energy states. Degeneracy pressure increases, but that increased pressure contributes additional energy to the gravitational field, which strengthens gravity further, which requires even more pressure, which adds even more gravity. This feedback loop becomes increasingly unstable as the mass grows. At low masses, the effect is small. Quantum pressure still wins. But as the star approaches the TOV limit, the feedback becomes overwhelming. Eventually, no amount of pressure can stabilize the star. The very force trying to save it ends up helping destroy it. The calculation that defined the limit. The existence of this maximum mass was first calculated in 1939 by two physicists, J. Robert Oppenheimer and George Volkoff. Building on earlier work by Richard Tolman, they applied Einstein's equations to the structure of ultra-dense stars. Their calculation revealed something remarkable. Neutron stars could not grow indefinitely. There was a maximum mass beyond which equilibrium solutions simply did not exist. Beyond that point, gravitational collapse was unavoidable. This result permanently defined the boundary between neutron stars and black holes. Observations confirm the limit. For decades, the exact value of the TOV limit remained uncertain. It depends on the equation of state of ultra-dense matter, the relationship between pressure and density inside the star. Because we cannot recreate neutron star conditions in laboratories, physicists rely heavily on astronomical observations. And those observations have provided increasingly precise clues. Several neutron stars have been measured with masses just above 2 times the mass of the Sun. One famous example is the Pulsar, PSR. J 0952-0607, whose mass is estimated at around 2.35 solar masses. Since this object clearly exists as a neutron star, the TOV limit must be at least this large. But other observations suggest it cannot be much higher. The neutron star collision that changed everything. In 2017, astronomers observed a historic event. 2 neutron stars collided. The event was detected by the gravitational wave observatories LIGO and Virgo collaboration. Also, the event is known as GW170817. The gravitational waves revealed that the 2 neutron stars had masses of about 1.46 solar masses and 1.27 solar masses. When they merged, the combined mass briefly formed a massive neutron star. But the object could not remain stable. Within about a second, it collapsed into a black hole. From this observation, physicists concluded that the TOV limit must lie somewhere around 2.2 to 2.4 solar masses, a surprisingly narrow boundary. The moment a neutron star dies. What happens when a neutron star finally crosses this limit? Imagine a neutron star slowly gaining mass from a companion star. Matter spirals inward. Layer by layer, the star grows heavier. The central density increases. Gravity strengthens. The pressure rises in response. But eventually, the star crosses the critical threshold. The equilibrium disappears, and collapse begins. Unlike the original stellar collapse that formed the neutron star, this process happens even faster. In just milliseconds, the interior of the neutron star implodes. The matter falls inward at a significant fraction of the speed of light. The density rises beyond nuclear levels. Space-time curvature becomes extreme. And then, something new appears. An event horizon, the birth of a black hole. An event horizon is not a physical surface. It is a boundary in space-time. Inside it, every possible path leads inward. Nothing, not even light, can escape. The neutrons that once resisted gravity with the stubborn rules of quantum mechanics are now trapped inside this boundary. Whatever happens next can never be observed from the outside universe. According to Einstein's theory, the matter continues collapsing toward a point of infinite density, a singularity, where our current understanding of physics breaks down completely. The neutron star has vanished. In its place remains only a black hole, an object defined by just 3 numbers: mass, spin, and electric charge. All the complex internal structure of the neutron star, its crust, its superfluid interior, its magnetic fields, disappears behind the event horizon forever. And yet, this dramatic transformation reveals something profound about the universe. Neutron stars exist because quantum mechanics can resist gravity. Black holes exist because eventually gravity becomes too strong to resist. And the boundary between them, the TOV limit, marks one of the sharpest transitions in all of physics. The final line between matter and collapse. The final stand of matter. In the vast universe, gravity almost always wins. It pulls gas clouds together to form stars. It shapes galaxies. It bends the paths of light. And when a star dies, gravity is usually the final force that determines its fate. Most stars end quietly, fading into white dwarfs. The most massive stars collapse violently, leaving behind neutron stars or black holes. But neutron stars occupy a very special place in this cosmic story. They represent the last possible form that matter can take before gravity becomes unstoppable. Where quantum mechanics meets gravity. A neutron star exists because of a strange rule discovered in the early days of quantum physics. The Pauli Exclusion Principle. This rule forbids identical particles, fermions, from occupying the same quantum state. From that simple prohibition emerges a powerful force, degeneracy pressure, a pressure that does not rely on heat, a pressure that does not fade as a star cools, a pressure that arises purely from the quantum structure of matter itself. This pressure is what supports white dwarfs. It is what supports neutron stars. And it is what allows matter to resist gravitational collapse at extraordinary densities. Inside a neutron star, the particles obeying this rule are neutrons, packed together so tightly that their quantum states fill every available configuration. Gravity pushes inward, quantum mechanics pushes outward. And for millions or billions of years, the two forces balance. The universe builds structure through refusal. There is something deeply elegant about this balance. The universe creates structure not by allowing particles to behave freely, but by forbidding them. Fermions refuse to occupy the same state. From that refusal emerges the structure of atoms. From atoms come molecules. From molecules come planets. From planets come life. And from that same refusal emerges the ability of matter to resist the most extreme gravity found in the cosmos. The same principle that prevents your hand from passing through a table is the principle that prevents a neutron star from collapsing. Quantum mechanics, discovered while studying the tiniest particles, determines the fate of entire stars. The edge of the possible. But nature always has limits, and neutron stars live exactly at that limit. They are the densest stable objects in the universe, the last structure that matter can form while still remaining matter. Beyond roughly 2 to 2.5 times the mass of the Sun, even neutron degeneracy pressure cannot resist gravity. At that point, the balance fails. The neutron star collapses, and a black hole is born. A region where space-time itself curves inwards so completely that nothing can escape. Not matter, not radiation, not even light. The boundary between two universes. This boundary, between neutron stars and black holes, represents one of the most important frontiers in physics. Below it, matter survives. Quantum mechanics shapes the structure of the universe. Above it, gravity dominates completely. The laws that describe the quantum world and the laws that describe space-time collide. And somewhere in that collision lies one of the greatest mysteries in modern science. A complete theory of quantum gravity, a theory that unites the physics of the very small with the physics of the very large. Neutron stars sit precisely at that intersection. They are laboratories where quantum mechanics and gravity confront each other directly. And for now, quantum mechanics still holds the line. Signals from the frontier. Every time a pulsar flashes in the night sky, it is sending a message, a signal that a neutron star exists. That somewhere in the galaxy, a mass greater than our sun is compressed into a sphere no larger than a city, and that quantum mechanics is still resisting gravity. Each pulse is proof that the Pauli Exclusion Principle works not only inside atoms, but on cosmic scales. The pulses travel across thousands of light years, across the Milky Way, across interstellar space, until they finally reach Earth. Tiny flickers of radiolight, evidence that matter can survive under conditions almost beyond imagination. Somewhere in the universe, right now, and even now, somewhere in the universe, the story is repeating. A neutron star in a binary system is slowly gathering mass from a companion star. Gas spirals inward. The mass increases, the core grows denser. The pressure rises. For years, for centuries, for millions of years. Until eventually, the star crosses the limit. And in a moment, shorter than the blink of an eye, the balance breaks. The quantum pressure that held the star together for eons fails. The neutrons that resisted gravity through every available quantum state finally lose. And gravity finishes what it started. The neutron star disappears. A black hole forms, and the universe becomes just a little darker. The last structure before collapse. Neutron stars are extraordinary not only because of what they are, but because of what they represent. They are the final structure matter can build, the last stand against gravity, the densest objects in existence that still possess internal structure, crust, core, superfluid oceans of neutrons, magnetic fields strong enough to reshape atoms. Beyond them lies only black holes, where matter loses its identity, where space-time itself becomes the dominant feature, where physics as we know it reaches its limits. A different way to see the night sky. So the next time you look up at the stars, remember that some of those distant points of light are not ordinary stars at all. Some are the spinning remnants of ancient stellar explosions, neutron stars, city-sized spheres of quantum matter, objects where the smallest rules of quantum physics control the fate of entire stars. They are among the most extreme creations of the universe. Proof that the laws governing subatomic particles can shape cosmic structures, and they sit quietly across the galaxy, holding the line between matter and the abyss, until the moment they finally cannot.